We learned in the last stage that every variable has a type that specifies what kind of information it can hold. The first types we need to learn about are called primitive types. Primitive types are the types the compiler knows about. Later on, we'll learn how to create our own types, but for now, we'll stick with the standard ones. You can tell that a type is a primitive type if it starts with a lowercase letter, and for now, we only need two. Variables whose type is int will hold integers, and variables whose type is double will hold real numbers. The fact that the compiler knows about primitive types means that the compiler can allocate space for them. It would make sense that you'd need a different amount of memory to hold a whole number, an int, than to hold a real number, a double, because real numbers have a fractional part. However, we don't have to worry about how much space that is. The compiler will handle it. Sometimes, moving data between variables is affected by the types of those variables. Integers are a subset of real numbers.
That's a massy way of saying that every integer is also a real number.
Okay, true enough. 42 is an integer, and 42.0 is the same number as a real number. Since every integer is a real number, we can store an int into a double without any concerns.
We can see that in our example. X is an int and Y is a double. We can put 32 into X and then store X into Y with no complaints from the compiler. Now Y will contain 32.0. Easy schmeezy.
That was easy, but the other direction isn't that simple. There are values that can be stored in a double that won't fit into an int. 42.5 is a real number that can be stored in a double, but we can't fit all of that into an int. There's not a place for that 0.5.
If we try to store a double into an int, our compiler will give us an error because it's worried that we're losing information. We need some way to tell the compiler, chill, man, it's okay to lose that information.
When we need the compiler to make a conversion between types, we do that by putting the type we want in parentheses before the value to be converted. This is called typecasting, and it basically tells the compiler to make the conversion. We understand the risks, and we want you to do it anyway.
If we think about this statement, y contains 42.5. When the compiler follows our typecast and converts it to an int, the result will be 42, and that's what will be stored into X.
That's right, Sumi. Typecasting from a double to an int will just drop everything after the decimal point. There is no rounding. There's one other important thing related to ints and doubles, the slash operator. It always means division, but there are two types of division, integer division and real division. Real division is division the way you've always known. Integer division doesn't care about the stuff after the decimal in the result, it just quits at the decimal point.
This feels like the two meanings of the plus operator. How will we know which one it does?
That's another good question. Like the plus operator, we look at the operands to decide what it does. If either operand is a real number, it will do real division. Only if both operands are integers will it choose to do integer division. In this example, x and y are integers and z is a double. We give x the value 42. In this statement, x and 8 are both integers, so the machine will do integer division, getting the value 5, and will store that into y.
Notice, it didn't round. It just quit at the decimal point.
In this statement, the division will be the same because both operands are still integers. The division will again evaluate to 5.
Remember, assignment statements evaluate the right-hand side and then store into the variable on the left-hand side. So the computer was not even aware that the value was going to be stored into z, which is a double, at the time when it was doing the division.
Exactly. When the machine stores that 5 into z, it'll convert it to a double and store 5.0 into z. Now, the right-hand side of this statement is different. 8.0 is a real number, so the slash will be real division, and the expression will evaluate to 5.25, and that value will be stored into z. If we have two values that are integers, but we want to do real division, we can typecast either one of the operands to be a double. That will force the slash to be a real division operator. So, in evaluating this statement, x has the value 42, which will be converted to 42.0. Then the division is 42.0 divided by y, which will be real division. Since y contains 5, 42.0 divided by 5 is 8.4, and that will be stored into z. One final thing about variables. Sometimes we don't want them to be able to change. In this lab, our code contains these statements. Inside each, you can see a declaration and an assignment statement. These are declaring variables and giving them values. In addition, the static final says the values cannot be changed by subsequent assignment statements, so the values cannot change when the system is running.
Why on earth would you ever want to do that?
Well, sometimes there are numbers that drive how our code works. In this case, the type of dice that we're rolling is defined by the constants min value and max value. If you look at the rest of the code, those constants are used in multiple places. Look at this portion of the code from the lab. See how the constants make it readable?
Readable schmeadable. Here's my code for this part. See how nice and concise it is?
Jejune, scattering all of those numbers around in your code is called hard coding the values, and it is highly frowned upon. Compare this line of code. See how the constants explain what we are multiplying by and adding, where the 6 and 1 aren't very descriptive.
But I know what they mean, so I can read it just fine.
If you were only writing small programs for yourself, that might be okay. But software engineers build big systems that last for a long time. That means there's a reasonable chance that you will forget what one of those numbers represents. In addition, software engineers work on teams. It isn't good enough for you to be able to read the code. Everybody else on your team needs to be able to understand it too. Readability is an important part of writing good code. The second benefit of the constants is that they make it easier to change those values later on. Suppose we wanted to change to a 20-sided die like they use in Dungeons & Dragons. If we didn't have the constants, we'd have to find all of the places that we had put in the 6 and change each one to 20.
If you look at the rest of the code, that 6 is used in a lot of places other than just the 2 we found here.
However, with the constants, we defined max value as a constant, so we only have to change the value in that one place, and everywhere we use it will be updated. In this video, we learned about primitive types, the types the compiler knows about. We learned about what happens when you convert between types and why you sometimes have to typecast to make those conversions. We also learned that there are two types of division. Integer division stops at the decimal point and happens when both operands of the slash operator are integers. If either operand is a real number, then the slash is real division, and it completes the full division. Finally, we learned that it's better to use constants than to hard-code values throughout your code. It improves the readability of your code and makes it easier to change those values later if we have to.